Hello, my name is Said Mohammad Hossein Musavi. I'm skilled in emotion recognition, image processing, data collection, optimization, and synthetic data generation. Also, I am founder and senior AI researcher at Cyrus Intelligent Research. This session is about human-centric evolutionary art through generative optimization and its explainability. Some key foundation for human-centric generative optimization. What is human-centric design? Human-centric design means creating processes where algorithms adapt to human emotion, perception, and feedback. Generative optimization is the fusion of generation and optimization. Algorithms such as the genetic algorithm search for visual or structural solution that balance beauty, order, and variation, guided by objective function or human input. Now, evolutionary art is a field where visual art evolves through iterative selection. Much like nature, images are generated, evaluated, and refined over many generations, producing new artworks that merge algorithmic exploration with aesthetic emergence. Just like any other problem, we have a definition of problem, the need, and finally the idea to solve it. Now, the problem here is traditional generative system, neural or algorithmic, often optimize for accuracy or efficiency, but not for aesthetic or human values. They miss the emotional meaning or subjective beauty that humans perceive intuitively. What is the need? Human-centric generative optimization connects computational power with human intuition. It treats the human as part of optimization loop, guiding, evaluating, and shaping outcomes dynamically. What is the core idea here? By allowing human feedback to influence algorithmic evolution, AI became a co-creator rather than autonomous generator. For example, human feedback can guide a Firefly or genetic-based optimizer to favor certain visual features, such as warmer, cooler palettes, smoother forms, or more balanced symmetry, embedding aesthetic intent directly into the optimization process. So what is the difference between heuristics and meta-heuristics? Heuristics are a simple problem-specific rule or search method that iteratively improves the solution using local information. They can easily get stuck in local optima and don't use global exploration strategies at all, like hill climbing, greedy search, local beam search, and more. Also, they are one candidate at a time. They might be faster, but not necessarily report as the best solution. Meta-heuristic, on the other hand, are a broader framework that guide or controls other heuristics to explore the search space more effectively, just like genetic algorithm. These includes randomness, population, and other parameters to escape local optima, like genetic algorithm, Firefly algorithm, differential evolution algorithm, particle swarm optimization algorithm, and more. So they are population-based, not just one candidate-based at a time. Both operate at the heuristic level, meaning they use experience-based strategies rather than exact mathematical optimization like linear or quadratic programming. But heuristics generate solutions, meta-heuristics search among solutions. That means more diversity. Now, normally we are looking for the global maximum, which is the highest value of the objective function across the entire domain of the problem, the best in case of the fitness function. In this slide, we can see some of the heuristic and meta-heuristic algorithms which are used in the project. For example, hill climbing from the heuristics, simply evaluate neighboring solutions and move to the one that improve fitness. Genetic algorithm is inspired by natural selection, where a population of candidate solution evolved through selection, crossover, and mutation to find the optimal or near optimal solutions. Firefly algorithm is one of the strongest algorithms out there. Simulate the flashing behavior of fireflies, where each firefly is attracted to brighter or better solution based on their light intensity, guiding the population toward global optima. PSO, or particle swarm optimization, is inspired by the social behavior of birds or fish, where particles move toward the search space by following both their own best position and the surround global base position to find optimal solution. Also, you can find the reference to each algorithm paper below. So traditional optimizers focus purely on numerical fitness, minimizing MSE, maximizing accuracy, or improving convergence. However, art, design, and creativity require subjective judgment that no metric fully captures. Human-in-the-loop optimize allow artists or designers to lead algorithms through aesthetic feedback. This transforms optimization from a mechanical search into interactive creative dialogue between human intent and computational exploration. Here we can see the flowchart of autonomous optimization and human-guided optimization. Optimization algorithm is interacting with solution with the input of machine. Human-guided optimization, here we have human and machine interacting with the optimization algorithm by feedbacks. So when we say quantitative evaluation from the fitness function, we are talking about metrics like mathematical ones like MSE, PSNR, SSIM, numerical score of how close the image is to the target. But when we are talking about subjective, emotional, or aesthetic judgments, it makes the color warmer, change the shape, opacity, size, and more. So basically it comes from the human perspective. So the workflow of the human-guided generative optimization is as follows. We have some input, which are target data, a target or image or abstract goal, which is loaded. Then the system initializes a blank canvas. Optimization engine uses a population-based or iterative search like PSO, genetic algorithm, or anything else like Firefly Algorithm, and generate visual candidates or shapes. Then we have machine evaluation, which each candidate is scored using quantitative metrics like MSE, SSI, PSNR, and more. Then we have human feedback loop, which user rates or modifies aesthetics like color, shape, opacity, and feedback biases the next generation of images. Final composition is the algorithm merges both human and computational feedback, and we achieve the final art. So feedback dynamics is as follows. We have initial phase, which random shape or pattern are generated. It could be rectangle, circle, triangle, polygon, and anything else. The system evaluates them with MSE, SSIM, and PSNR. We have the optimization loop. The algorithm adjusts parameters like position, color, rotation, opacity to minimize the error. In each iteration, fitness improves. That means the error decreases. Then we have the feedback injection stage. At fixed intervals, human feedbacks modify to search direction. Examples is increasing warmer colors, add symmetry, reduce opacity, and more. The optimizer blends human feedback with numeric fitness by the following equation: alpha multiplied by error plus 1 minus alpha multiplied by feedback. Convergence is the system stabilized as both aesthetic, subjective, and the computational objective goals align. This is a feedback fitness combination formula: alpha multiplied by E objective plus 1 minus alpha multiplied by 1 minus human. We are looking for new effective error or fitness value. Our objective error, E objective, is our objective error like MSE. S a human is human feedback score between 0 to 1. Alpha is a weight balancing between machine accuracy and human preferences, like for example 0.85. Then we have interpolation. The algorithm reduces MSE but also listens to the subjective human judgment feedback. So even if the image is not pixel perfect, if the human likes it, it gets the reward. Now we start the algorithmic part and some results. This is a result you can see from Firefly Algorithm on an aesthetic base without any target images. So it is a Firefly Algorithm-based generative art program, specifically a Firefly aesthetic generator. It evolves abstract visuals patterns by optimizing aesthetic metrics: symmetry, color, balance, composition, color variance, and etc. Using the Firefly algorithm, it creates new artwork that maximizes aesthetic quality through iterative optimization. The fitness function evaluates how well an image meets aesthetic principles of harmony, structure, and variety. The spiral colors visualize how fireflies cluster toward the most visually attractive center of the search space. As you can see, each result is the output of separated run with different parameters. Now we get closer to the main purpose of this research. Here we can see a heuristic algorithm called hill climbing try to reconstruct the target both at the right using just rectangle. As we can see at top left, it starts with some basic rectangles going forward to the right, to the top, to the bottom left, and finally to the bottom right. So basically it tried to reconstruct the both image, and it was somehow successful just using a rectangle in 200 iterations. Also here we can see genetic algorithm trying to reconstruct the Damavand mountain, which is located at Tehran, Iran, using just triangle from top left to the bottom right. We can see how it tried to reconstruct. As we can see from just pure triangle, it finally achieved some results. Obviously, by increasing the iteration, it could reconstruct the image fully. But here it's just it has an educational purpose, so we are just showing the process. So here we had like 500 iterations. It took like 35 minutes with the Core i7 system, but it could be even better. Or here we can see that Firefly algorithm tried to reconstruct the Cyrus image as a target. You can see it in the right, just using polygons, but polygons have different edges. So basically in each run it's going to randomly take a number of polygons between 3 to 7, and finally we can see from almost nothingness to a similar face. Or here the helmet image is constructed using just lines. Here we had more runs, like 3 hours of running, so the image is much more close to the target using PSO algorithm. Here is another PSO algorithm reconstruction, but we used 3 different elements of line, ellipse, and triangle to reconstruct the lone image. As you can see at top left, it is just basic circles, lines, but when it goes forward, it's going to reconstruct the face. And now we reach to the human-guided multi-shape PSO art, which is a combining of optimization and aesthetic feedback. So the feedback comes from the human using the evolutionary algorithm of one of the metaheuristics, which is the PSO, and finally we have the art. So PSO is inspired by the social behavior of bird or fish, where particles move through the search space by following both their own best known position and the swarm global best position to find optimal solution. At the right, we can see the flowchart of this algorithm. It is one of the most well-known algorithm, which is very strong, also very fast. So basically, it could be applied on any application without failing. So in PSO, each particle in PSO represents one possible shape, contributing to the whole image. After deciding on the shape, we have the following parameters for the specific shape. For instance, when we feedback at and say rectangle, we have x and y, shape center on the canvas, and then we have w and h, which is width and height. We have the rotation of theta. We have RGB, which are color channels, and we have alpha, which is the opacity level. So each particle is consisted of 9 elements of x, y, w, h, theta, r, g, b, and alpha. So this is a nine-dimensional space. Each particle tries to find parameters that reduce the difference, like MSE, between the rendered canvas and the target image. So here in this table, we can see the PSO concept values of each parameter of PSO and mathematical rule and its equivalent in painting and art. For example, when we have particle X, so in a mathematical rule, we have to conjugate a solution in a search space, but its equivalent is shape parameters with those 9 factors where to draw and how it looks. Or when we say velocity, in a mathematical rule, we have direction and speed of the movement in the search space, but when it comes to the art, It means how quickly the shape, feature, size, color, and position change between iterations. When we say p-best, we are talking about the best solution founded by each particle, but the art part says the particle's best version of the shape that produced the lowest error with target, and so on. So for example, what swarm means all particles evolving together. In the art section means all candidate shapes competing, cooperating to paint one optimal brush stroke. So in PSO, in the particle evaluation, each particle adjusts its parameters, position, size, color, opacity, to PSO's velocity and position updates. It learns from own best results, which is p-best, and the swarm best results, which is g-best. So then we have iterative compositions for every shape. PSO finds the best version of that shape type. Also, the best, which is a global shape, is rendered on the canvas. Canvas updates and PSO restarts for the next shape. Gradually, the image accumulates. Then finally, we have the evaluation and feedback. For that, we need the fitness, which is the MSE here, between the canvas and the target. Human feedback modifies PSO's direction, favoring certain shapes, colors, or opacity levels for aesthetic improvements. Here we can see the real example of an experiment using this system on baboon image. So we can see from top left to the bottom right that how the image is evolved, and finally try to reconstruct the baboon face at the bottom right corner of the slide, which is the target. So first shape is the rectangle, iteration is 13, human feedback. Now so basically the program works like this. It's gonna run after the few iteration, it's just receive the feedback from the human. So it asks how much good it was. So for example, here I just entered 0.4. That means it was below half to me. So it asks the human shape, what shape? So I change it to the triangle with 0.5 ratio. That means the effect of amount of triangle to be combined with the rectangle, which was before. Then it goes 30 more iterations with triangle and rectangle. Then it asks the human rate, a little bit better, 0.5 human change. So I changed it to the warmer colors with 0.6 ratio. Then it asks for another feedback from the human at the 19th iteration. Still the shape is triangle. So it's a little bit better to me. So I just enter 0.6 human change. I changed the opacity to 0.5 ratio. Then at the iteration 120, it asks for what changes. I just said use the circle. So we had the rectangle and triangle. Now we had added circle. Human rate of 0.7. So basically I was satisfied like 0.7 out of 1. Then we have the human change shape to circle with the 0.8 ratio. At the end, we can see the difference with the final result of the project at 120 iteration with the targets improved. So basically our error just went down from 0.012 to 0.006, and our PSNR improved from the 19 to 22. Also, same as SSIM, which is from 0.30 to 0.50. That means a lot of improvement happened. So it is the aesthetic form. Also, it is trying to reconstruct the target image. So we are going to cover some of the explainability parts. So for example, here we start with some basic XAI algorithms. So explainability reveals why an AI makes each decision. So explainable AI or XAI turns complex models into understandable elements for humans. Here, fitness shows how the base image is reconstructed, the baboon image. So fast convergence here means the target image foundation is made in the early iterations. Here we have error reduction by each shape. So we have delta error here. Each bar here shows how much a single shape reduced at the total MSE. Early rectangles cause steep error drops, triangle refine the local texture, and circles providing a smooth blending. Delta error shows change in MSE after adding each shape. So if you can see closely to the image, we can see that each 13 iteration, we have some changes. So here from 30 to 60 to 90 to 120 and 160. That is why all of them are flat out in those iterations. It tells how much that a specific shape improves the image. A higher error bar means each shape contributed positively to reducing the total error. So here we have parameter variance, which is an explainability plot. The angle has by far the highest variance, meaning it changed the most across all shapes and had the strongest influence on reconstruction. Color channels of RGB and position X and Y vary only slightly, so they fine-tune rather than dominate. Width and height and opacity barely vary, so they contribute little to the optimization. The algorithm relies mostly on rotational adjustment or angle to fit the shape, while color and size remain relatively stable. So here we have shape placement heat map. Each color square represents a region of the image canvas. Brighter red, yellow-white indicate a higher density of shape, meaning the algorithm focused more there to reduce reconstruction error. Darker regions were less frequently updated, showing those areas either already matched the target early or contributed little to further improvement. So it shows which parts of the image the PSO-based process found most important for matching the target. So here also we have opacity and color trends over time. The plot shows the evaluation of color and opacity for each generated shape throughout the reconstruction. The black line opacity shows how transparent each shape was. The R, G, and B curve fluctuates strongly, showing that the optimizer continuously explored different color combinations to best approximate the target texture and tones. Now we're gonna explore some of the most advanced XAI algorithms on this project. So we have the permutation, for example. Permutation explainability checks how important each feature really is by seeing how much model's accuracy drops when that feature's value are mixed up. So we have 9 features in total. In permutation explainability, the algorithm tests each feature one by one. It randomly shuffles mixed up the features' values across all samples, then measures how much the model's accuracy drops. This process is repeated many times, here 20 times for reliability, and the average performance drop is reported as the feature importance score. So here we can see that the permutation feature importance shows the opacity as the dominant feature. Opacity dominates as the most influential parameters. Small changes in transparency has the greatest effects on the reconstruction accuracy. Height and green channel contribute modestly, while spatial and color coordinates show minimal influence. Also, we have another advanced XAI algorithm called LIME, or Local Interpretable Modeling Agnostic Explanation, which explains why the model made a specific prediction for that one sample. It has slightly changed the sample's feature values and observed how the output shifts, building a simple local model, like a small linear one, to approximate the behavior. In short, LIME shows which feature matters most for that one shape or instance, not globally for the whole model. So basically, permutation importance checks global influence by shuffling one feature across all samples and seeing how much model performance drops. It tells you which feature matters overall. LIME looks at one single prediction and slightly change the input locally, add small random changes to learn which feature most affected at that one result. So permutation explains the whole model's logic, while LIME explains one specific decision. Here we can see the LIME plot. The LIME plot shows how individual features affected one sample's prediction. Here, opacity strongly increased the model's confidence, while other features like RGB and geometry like H, W, and angle has a smaller or negative effects. In short, it means that local decisions for this shape was driven mainly by opacity value. The sample 5 here is the 6th rectangle inside the test set. So both permutation importance and LIME identify opacity as a dominant factor. That means the model is consistent. Opacity strongly influences both global behavior across all shapes and local prediction for that one sample. Thank you so much from you all for your attention to this presentation. and it has been a pleasure sharing this journey of optimization and explainability. So in order to download the materials, copy and paste these text into your and find the repository section, the Human-Centric Evolution art. Here we can see the repository, including some explanations and all the codes for different. Then you can download the code or the repository. After downloading, you will find such a folder, different type of evolutionary art methods. Let's run them one by one. For example, this is the number one, which Firefly Algorithm is going to generate the evolutionary art from scratch. It's going to start working. All 23 cores are at work. It takes some time. At the end, we are going to get something like this or this. Also, we have all other results from different algorithms. And this one is the last one, which is the human feedback one. So for example, here, when we run the algorithm, it's going to start from iteration 0. After a while, after 13 iteration, it's going to ask for feedback about the result which is produced so far. And it's going to repeat that every 30 iteration. I'm going to fast forward. Okay, now we are at the iteration 13. It generates first image of the bubble face. As you can see, it's just used rectangles. And it is asking about my feedback. I'm going to rate it like 0.7. Then it asks for what type of change we can make. We can change the shape, color, opacity, size. I'm going to say shape. What shape? Circle. How much? Like a lot circle. Then it's going to continue the same to the iteration 16, showing a new image and ask me for another feedback. So I'm going to stop this. In the basic XAI and advanced XAI, we have some explainability. So for example, this one, it's going to generate some as we had in the slide. Same for the advanced. So you can see that we have different results. Results are changed because we run the program, the main program, and it stopped in the middle. So these results are not that reliable as the iteration stopped immediately.